What's up, all you badass mathematicians? So today we're going to talk about related rates, and we're going to look at an example. So air is being pumped into a spherical balloon at a rate of 9 cubic centimeters per second. What is the rate of change of the radius at the instance the volume is 36 pi centimeters cubed? So before starting these problems, we should clearly state our goal so that when we're finished, we can verify if we've accomplished what we set out to do. So our goal here, we're trying to find the rate of change of the radius, and we're trying to figure out exactly how quickly the radius is changing when the volume is 36 pi centimeters cubed. So we're trying to figure out how fast the radius is changing. So if we're talking about quickness, we're going to figure out the change in radius with respect to the change in time. So this will be our goal. So looking at the information we're given, we see that we're given the rate at which the volume is changing with respect to time, and we're given a specific volume. So the key thing here, we want to figure out a way that we can relate the radius of the balloon with its volume. And one way we can accomplish this is through the equation of the volume of a sphere, 4/3 pi r cubed. So here we have our volume, and here we have our r, and this equation gives us our relationship between our volume and radius. So at some point we want to figure out what the r dt is, and right now we know what dv dt is, the change in the volume with respect to time. So next, we need to figure out a way to relate these rates. How is the change in volume related to the change in radius? So we can accomplish this by differentiating both sides with respect to t. So we're going to do d dt of our left side and d dt of our right side. So this means on our left side we have dv dt is equal to 4/3 pi times 3r squared, and we can't forget the chain rule, times dr dt. So it's very important that when we're taking our derivative with respect to another variable, we remember the chain rule. So here the derivative of v with respect to t is going to be 1 times dv dt. And then similar here, the derivative of r cubed with respect to t is going to be 3r squared, and then chain rule will give us our derivative of r. So now we know that our value of dv dt is 9. So we can write 9 is equal to 4 pi r squared dr dt, which means that dr dt is equal to 9 over 4 pi r squared. So we have an expression for dr dt in terms of r. So now we need to figure out what r is going to be. So here we have an equation to relate V and R, and we're actually given a specific instance of the volume. So we can actually write that 36 pi is equal to 4/3 pi r cubed. So this means that 9 pi is equal to 1. We can cancel out the pi's as well. So 9 is equal to 1/3 r cubed, which means 27 is equal to r cubed, and r is equal to plus or minus 3. But because we're talking about a balloon, a physical object, we know its radius is going to be between 0 and well, I guess it could, up until it pops. So this actually, there's no need to have a plus or minus. So our radius is just going to be equal to positive 3. So this finally means that we can box and ship this in for this value of r, leaving us with dr dt equaling 9 over 4 pi times 3 squared. Which means dr dt is equal to 1 over 4 pi, and always remember units, centimeters per second. And now to check back with our goal, we're trying to find the rate of change of the radius when the volume is 36 pi cubic centimeters. So now that we have an actual value for dr dt, we have finished the problem. Alright, thank you for listening, and if there's any questions or feedback, please feel free to leave that in the comments. Thank you.